Good afternoon. It's good to be back home in Denver. My name is Jake Schwartz, and today I'm going to talk about networking and persistence for mobile applications at scale. I got my start programming when I was 8 years old, where I made my first website. Do you guys remember when the web looked like this? These under construction GIFs littering the web, and I can assure you my website had at least one of these, and it was under construction the entire time. I eventually went to study computer science at the University of Michigan. This opened up a lot of opportunities for me, like going to work at Apple. I worked at Apple for 2.5 years on the Mac OS X software team. This was a really tremendous opportunity, and I loved the people that I worked with, and I learned a ton. Although eventually I got bored of Apple, I left to do startups. I joined up with some folks to make a venture-backed social networking app, sort of like a matchmaking app. A 1.5 years later of this, we got acquired by a company called Life360. What is Life360? We make an app which is like Find My Friends for families. It's a social network for families. It's cross-platform. It's a top 10 social networking app. We're hovering between 9 and 12 in the ranks for social networking on the App Store. And just last week, we hit 10 million monthly active users, which has been super exciting for us. The app is available for download around the world, localized in 13 different languages. Now, we've been growing pretty tremendously over the past few years, and it's been really exciting, but also presents a lot of challenges. The challenges of scale. To give you an idea of the sort of scale we're talking about, our servers handle over 1.7 billion mobile API requests from our Android and iOS clients every day. So that's super huge and presents a lot of challenges for our server and infrastructure teams, and also challenges for the client teams as well. And that's what I'm going to talk about, the challenges we face for developing at this scale on the mobile side. And then we'll talk about how we can solve some of these challenges by using what's called a ModelStore. And then we'll dive into what a ModelStore looks like and see what's under the hood. Let's take a look at some of these challenges that I talked about. At Life360, with 10 million monthly active users, mobile data usage and battery consumption are extremely important to us and to our users. If our users find that our app is using too much of their power or too much of their cellular data, they'll simply uninstall the app, and we don't want that. These effects are magnified at the scale that we are. We actually see people tweeting about us if we use too much of their power or leaving bad reviews in the App Store. So we're very conscious about the resources that our app consumes. Additionally, users have come to expect their data always when they want it, which is why we think about caching and persistence on the mobile side. And finally, as engineers, we want to constantly upgrade our code base as the market changes, as the product changes. So how do we make these upgrades and these changes to our code base while at the same time providing a quality experience to our users? We're going to dive into that a little bit. How do we update these technologies in our code? First, I want to see a show of hands. How many of you all use core data in your apps today? A lot of people. Keep your hands up if you love to use core data. Okay, way fewer people. Thought so. How many people have heard about Realm and might consider it for their next project? It's another database technology. Great. So we're going to look at this sort of upgrade. If you're using core data in your app, how can we swap this out to use Realm in a way that doesn't introduce bugs? And to do that, we're going to look at an example. Let's say we're developing an app, perhaps seeing members on a map, members of my circle. Our app's going to make a network request to the server to retrieve these locations for these members. And let's say we want to see these members moving on a map in real time, so we'll introduce some sort of polling mechanism. Perhaps every 30 seconds, the app requests these locations again. And then we want to provide an offline experience for our users. So if they drive through a tunnel or right when they open their app, before the network request is completed, they have their data available. And this is why we introduce a database. Let's say SQLite in this example. Now, our app is more than just one network request. Like many of your apps, it's quite complex, and there's a lot of client-server communication. We have many points in our code where we make requests to the server, perhaps database-backed requests like login and sign up, off, sending a message to other users in the app, or changing my avatar URL, for example. So our code has all these touch points, and let's say we want to upgrade to core data. We then go through and find each and every one of these points where we touch SQLite and change all these references to use core data. And we might miss a couple along the way, but that's okay. We'll find them eventually, or our users will. And this was okay. We are now using core data to back our network requests. But then let's say one day Realm comes along, promising faster database accesses and cross-platform code and a shinier, new, easier development experience. So again, we go through each and every one of these places in our code where we reference the core data database and change this all to use Realm. And then let's say we want to provide our users with a more real-time network experience, so the app feels a little faster. So we change all of our NSURL session references to use WebSockets. Again, going through each and every point in our code where we reference NSURL session, changing this over to use WebSockets. This is relatively error-prone, as you might imagine, especially as your app grows and you have a lot of legacy code and a lot of references to the network and to the database. In some of the code bases I worked on, I couldn't imagine making these changes. So at Life360, we upgraded to use core data a few years ago when it came around to the scene. We were using our legacy data store, which was actually flat files on disk. And we upgraded to core data. Can you guys guess how long it took us to adopt core data in our app? It took us 2 years to do this. And this was not necessarily 2 years of full-time work. It was sort of part-time, ongoing effort to change all of our model objects to use core data-backed entities, to develop the XC data model, a rather complicated topology in our case, and also to solve all these context and threading bugs that, of course, came along with core data. So 2 years later, we're finally on core data, which is great. But then we looked at this and said, we're probably going to want to upgrade our database to some other technology another time, perhaps next year or a few years later. And we don't want it to take another 2 years. So wouldn't it be great if there was a way to organize our code in such a way that facilitated these upgrades and made them a little less error-prone and, of course, faster? So we can organize our code in such a way that we sort of sweep all this stuff under the rug, the references to the network and direct references to core data. And our UI simply references this model layer. The UI doesn't have to care about how it touches the network or how it saves data to disk. It simply asks its model layer for the data that it needs. This allows us to think about our code base in two parts. We have our user-facing features, things that the user sees and touches. And then the networking and persistence code under the hood, all of the code to provide the data to support the UI. I call this a bicameral code base. When you have your user-facing features entirely decoupled from your networking and persistence code. Above the line, we have things like map pins and chat UI, a login screen, a sign-up screen, that sort of thing. And below the line, we have our networking and persistence code, core data, NSURL session, WebSockets, our older database, or any sort of retry or network queuing that we may need. We can further abstract the networking and persistence technologies into what's called a model store. What is a model store? A model store is a data engine for your application. It has 5 capabilities. A model store provides network syncing for your app, that is updating data from the network, and then saving this data to disk, persistence. It also allows for consumers to fetch and query this data, and then it notifies consumers when this data changes. And lastly, a model store allows for mutation of this data, that is, inserting, updating, or deleting model entities. If you're familiar with reactive programming technologies like RX Swift or Reactive Cocoa, you may know that requesting data and listening for changes is sort of the same thing. You just subscribe to an observable. So we can use RX Swift here and combine these two capabilities into one, and we call that the data stream. So these are the 4 capabilities of a model store: network syncing, persistence, the data stream, and allowing for data mutation. A model store provides these capabilities for a domain-specific entity. What do I mean by that? Let's look at an example. The member store is a type of ModelStore that provides these capabilities for members to support, let's say, the map UI that we saw in the earlier example. It allows for syncing and updating of members from the network, like their location information, persisting them and saving them to disk, and providing the data stream and allowing for mutation. The ModelStore maintains your data so the rest of your app doesn't have to. Let's look at a quick example. This is a very simple prototype that I built to use a ModelStore. I made a very short recording of this. It's simply a map which uses the data from a ModelStore and shows these locations on a map. So this connects to the Life360 servers using a real circle. These are some of my coworkers. And it gets these data updates. And you can see the data stream in action as I zoom in on this guy driving on Highway 280 to San Francisco. And you see him moving in real time. And this real-time movement is something that our users have come to expect in recent years. It's sort of table stakes for any good live app. Let's take a look at how I built this. This is the code that I wrote in my UI view controller, which owns the map, to get the data. I'll go through this step by step. First, I instantiate a ModelStore, telling it to use core data for persistence and WebSockets for network communication. And then I grab the getAllMembers stream. If you're familiar with RX Swift, you'll feel right at home looking at this. If you're not, just know that an observable stream is a lot like delegate callbacks. When the data changes, this callback will be called again. And this is a stream of members that is an immutable struct, which we then map to a stream of map pins. A map pin is our view model, which we eventually send to the map. It takes the coordinate, the avatar URL, and the first name of the member, and then returns that, thereby mutating the stream into a stream of map pins. Next, we subscribe to the stream and feed each of those map pins into the map. And finally, calling disposed_by. This is simply RX Swift's way of doing memory management. When this view controller goes away, this stream will go away. This is the code that I wrote to accomplish what you saw on the map, given that I have a ModelStore in place. It's very simple, and it was extremely easy to write that. And notice that I'm doing no core data fetches, no perform block and wait, none of that threading nonsense. I simply take this stream of members and connect it to the map. What you just saw is above-the-line code. It's UI code, consuming below-the-line code, the networking and persistence. That's how we maintain this decoupled bicameral codebase. And a bicameral codebase has many advantages. Decoupling your code in this way allows for upgrading technologies in a way that doesn't introduce bugs. So for example, in the code that you just saw, imagine me upgrading from using core data to using realm. Would the view controller have to change? The code wouldn't have to change at all, because I'm simply observing the stream of members. Also, fewer bugs and better testing. Imagine unit testing the ModelStore. You don't have to use UIKit or UI view controller or have an app delegate or anything like that. And likewise, unit testing the UI view controller code, the code that you just saw, you simply mock out a ModelStore and make sure the map gets the right view models. And when you're developing using a ModelStore, as you saw, it's super easy for me to make a map use the real data, just subscribing to the stream. And other such features that may use members in the future. Imagine a profile, making it live update, or any sort of settings page or anything like that, or chat UI. So that's faster feature development. Now imagine making additional apps. If you want to spin off other apps, and you have a ModelStore built, you could just reuse this if you want the data from your ecosystem to live in all those apps. And furthermore, when you have your code isolated into these two parts, people can begin to specialize in developing for certain areas of this code. For example, if you have somebody on your team who really loves animations and user interaction, they can do that without having to think about core data. Likewise, if you work with somebody who loves data structures, algorithms, and network connectivity, they can specialize in the below-the-line data code. I'll pause here and tell you why I'm really giving this talk. And it's sort of a selfish reason. It's because I love developing animation code. I love working with UIKit. And I really don't like working with core data. I don't know if you detected that. And so that's why we started the ModelStore project at Life360, so that we can have this data layer in place, so that we can work on UI code independent of data code, and vice versa. Now, when you have your code isolated like this, and people begin to specialize, that also has hiring benefits for your team and for your company. You can start to attract people who are, say, experts in WebSockets, who don't really like dealing with core animation or UI, or layers or anything like that. You can attract people who are killer animation code writers, for example. At a startup, we tend to prefer to hire generalists, although having this option available to us is nice. So those are some of the benefits of using a bicameral code base and using a ModelStore to kind of separate this and create this line between your UI code and your data code. Next, let's dive into the internals. How does a ModelStore work? A ModelStore necessarily has two main components, the networking and the persistence. We can further abstract these into a local store, which abstracts the database, and a remote store, which abstracts the network. These are classes which the ModelStore owns, and again, simply abstracting the database and the network. This is what allows us to swap out technologies. You may have a core data local store and a realm local store. Swapping one for another is super easy here, and you won't have to change any code, any of the ModelStore code or any of the UI code. And you may even want to experiment with them or A/B test if one introduces bugs, for example. Let's see how the ModelStore accomplishes its four capabilities: network syncing, persistence, providing a data stream, and allowing for mutation. Our member store, for example, may make a fetch from the network, get me member locations. So it makes this request from the network and then tells its owner, its parent, the ModelStore, that it got some data. The ModelStore then maps this data and feeds it directly into the local store. The local store, again, abstracting away the database, saves this to the database. Separately, the local store notices that something has changed in the database, perhaps through a contexted change notification. It gets this change and propagates this outward to consumers. First, its parent, the ModelStore, and the parent then propagates this outward to its consumers via the observables. This is a unidirectional data stream, which itself has its own benefits. Mutation is done in a very similar way, just the other direction. An edit to a resource or a deletion or an insert is done first through the local store, which notices the change, tells its parent, and then to the remote store. The remote store abstracts away all of the networking stuff. It talks to the network directly, and it's the one that deals with GET requests or WebSocket subscriptions or anything like that, so that the ModelStore and any parent up the hierarchy doesn't have to. That's a quick look at how the ModelStore accomplishes its four capabilities. Let's look at some code. So there's a lot of code on screen, but it's quite simple, and I'll walk you through it. This is the protocol definition for a ModelStore. I want to point out a few things here. First, you see activate and deactivate at the top. These are optional. These are just messages that you can pass to the ModelStore from your consuming app to tell it when to start and stop its syncing mechanisms, perhaps when the user foregrounds the application or backgrounds it. Next, notice that the create, update, and delete functions all return observables. Again, this is RxSwift. They don't return response code or any sort of asynchronous callback. It's an observable stream of type result. This allows consumers to know when the result is pending, successful, or an error when they make these updates to the data. And this is a very simple CRUD interface. You see create, read, update, delete. Now, also note that this is a generic protocol. Using Swift 3 syntax, we assure that every ModelStore necessarily has an entity type. For example, a member, or a chat message, or if you're Sarush building the Beacon app, an event nearby. So every ModelStore is of a specific entity type, and you'll see that reflected in the API definition. So that's a quick look at the API definition for the ModelStore protocol. I want to point out that the ModelStore abides by this protocol, and the local store and the remote store. Everything provides this CRUD interface to its respective data. The local store maps the database to a CRUD interface. The remote store maps the network to a CRUD interface, create, read, update, delete. It's CRUD streams everywhere, if you will. So that's a look at the internals of a model store and the API definition and the architecture. You may be asking, do we use the model store in our app today? And the answer is yes, we absolutely use the model store in the iOS app, and we use it in our Android app. So rather than fighting with our friendly developers on the other side of the aisle, we've collaborated with them, designing and implementing the model store together, in sync from day one. This has a number of benefits for us. We've essentially doubled our team's software design capacity. Rather than having 7 iOS engineers and 7 Android engineers, each developing their own system in their own respective corners, we're developing the same system with 14 mobile engineers. We do so using shared wiki documents, like the architecture diagrams that you've seen, and the model store protocol definition that you've seen as well. There are a few technologies that help us maintain this parity between platforms. RX Swift and RX Java, aside from being absolutely amazing technologies in their own right, highly recommend them, also have a lot in common with each other. They're, in fact, identical technologies almost. It's just a little more semicolons on Android. RX Swift and RX Java are both ReactiveX technologies, so they share the same massive corpus of documentation and super helpful community. The added benefit here is that we have a lot of RX experts on the Android team, so I can go and ask them for help, and vice versa when we're working with the same technologies here. Realm, of course, being written in C, is another technology that we share between iOS and Android. It just helps us speak the same language when we're designing and developing the model store. And finally, we have a shared architecture. Although we don't share any literal code between the two apps, we are very strict in maintaining the same architecture down to the names of the classes and names of variables. Any change to the architecture means it's reflected in both the iOS code and the Android code. This helps us get the benefits of shared software design. We took a look at some of the challenges that we face when developing at scale, like how do you swap out different persistence or networking technologies while still maintaining a high-quality experience for your users. We looked at how we can solve some of these challenges by introducing a model store, and that helps us decouple our UI code from our networking and persistence code. And we took a look at some of the benefits of a bicameral codebase. And finally, we dove into how a model store works by looking at the architecture diagram and some data flows, and also the protocol for its interface. I hope this has been enlightening for you, and that you may try a model store in your next project. Stay tuned at our blog at engineering.life360.com for more updates. We'll be writing some articles on the model store. And please feel free to email me at jake@life360.com. I want to thank our organizers and all of our volunteers for the opportunity to speak here and sponsor this conference. Thank you. Any questions? Yes?
Did you ever have to switch, make any big changes like you did with core data to Realm? Do you have to do similar stuff on the backend side, like from HTTP or REST to WebSockets, or was it always the same architecture throughout?
Yeah, good question. So the question was, we made some of these technology changes on the client side. Did we ever make any of these technology changes on the server side as well to support some of this? The answer is yes. So we're using something similar to WebSockets. It's called MQTT, which is kind of publish, subscribe. And this allows us to get this real-time location experience in the app. We had to do a lot of work on the server side to support this. Luckily, it was relatively easy for us to swap that out, like polling of an HTTP request for an MQTT subscription. On the server side, they did build an MQTT broker and an authorization service as well. Yeah?
Yeah, so one question I have was, did you guys come up with this concept yourself, or is there like a lot of thinking on there on the same topic?
Yeah, good question. So the question was, did we come up with this ourselves, or is this, where did this idea come from? The concept of ModelStore is borrowed from a lot of different places. It sort of arose from this challenge that we had in upgrading our core systems. We knew we needed at least one abstraction layer. And then we said, well, let's bring the network into here, and then we'll just make it a data layer. To my knowledge, I haven't seen any writing on that specifically, and then like the concept of the bicameral codebase. I'd be interested in seeing any if it exists out there. Yeah?
Are you familiar with Redux, flux pattern, and how does yours differ if you're familiar?
Yeah, awesome. So the question was, am I familiar with Redux and the flux pattern, and how does this differ? I don't have direct experience with Redux or the flux pattern. I do know that there is some mechanism which maintains state. Is that right, in Redux? The ModelStore, or an instance of a ModelStore, may be that. Maybe the thing that maintains state. I think of it as a little more encompassing. When people talk about Redux, they often refer to this state machine for a particular class or set of classes. You can think of a ModelStore as more of a state machine or maintainer of state for your entire app, or a portion of your app. Yep.
Have you been happy with the overall performance of React at scale?
Yeah, good question. The question was, Realm. Yeah. Have we been happy with Realm at scale? So we haven't turned on the Realm aspect, the Realm component yet for our users. We are happy with core data once we resolve all the threading issues. So I'll get back to you once we flip on the Realm switch. Other questions? All right, thank you.